So now we get to talk about calculus for power series. And so you probably, I think most students are happy at this point because we stop talking so much about convergence and divergence and we start talking about methods of calculation again, right? And ultimately, really what we're getting to is the larger point of why we're doing these things, in some sense, is to apply, power series to model functions. And so that's very, very nice, because if we can take a function and replace it with a power series, then power series is essentially a polynomial without end, and it allows calculus essentially just like polynomials. And that's this theorem, is that to differentiate a power series, you do exactly what you'd expect. Namely, the derivative of a power series, we just differentiate term by term. All right. The integral of a power series, we just integrate term by term. So, let's see here. So this theorem allows us to integrate functions by integrating their power series representation. Alternatively, expands the scope of the geometric series result. We'll see both in the examples in the next several pages. Here's a good example on how it allows us to do integrals in a kind of weird new way. If we wanted to integrate dx over 1 plus x cubed, we could have before. It would have been partial fractions. It would have been pretty tough, though. On the other hand, we can look at 1 over 1 plus x cubed as being a geometric series, right? It's got a equals to 1, and the radius is minus x cubed, which gives us minus 1 to the n times x to the 3n, all right? Provided that the absolute value of x is less than 1. And so I can integrate this function by integrating its series representation, its Maclaurin series representation. And I get that. So that's it. I've integrated this function by just integrating the series term by term. That's pretty awesome and like really, really different than what we've done up to this point, right? Now, I should also mention that we can look at this in terms of the plus dot 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 notation, and maybe that's even better in some sense. See, because you can see better why it's called term by term calculus if we use the plus dot 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 notation, right? Like 1 dx over 1 plus x cubed is the integral of that. That's the geometric series that represents 1 over 1 plus x cubed, and then integrating term by term gives me x minus a quarter x to the fourth plus a seventh x to the seventh, so forth and so on. Since it's an indefinite integral, I have to add a constant. Since I forgot to add it at the start, I added it at the end. Okay. But anyway, that's term-by-term calculus theorems. And so now I have, I'll show you how we combine this term-by-term calculus idea with the geometric series idea. All right. So here's, and the numbering here refers to some old handwritten notes I have in calculus too. And I've decided to leave the numbering just for the sake of reference. So here we go. I have entitled this Power Series and Geometric Series Tricks. So if I had f of x as x minus 1/3 x cubed plus x to the 5th minus dot 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 dot, we can use a theorem to get a geometric series. So like the derivative term by term is 1 minus x squared plus x to the 4th, and so forth, right? So the derivative term by term of that series is this series. But hey, that's a geometric series, so I can rewrite that as 1 over 1 plus x squared, because I've identified that the first term is a, obviously, and to get each successive term, I multiply by minus x squared, right? So the radius of the geometric series is minus x squared. But on the other hand, to get back where we started, we can integrate the derivative, right? And the integral of 1 over 1 plus x squared is, well, you know it, you love it, it's the inverse tangent. So you have inverse tangent plus a constant is equal to f of x, all right? But on the other hand, f of 0 is 0 for the original function, right? And the inverse tangent is 0, 0. So this shows me that that constant is in fact 0, and we've got f of x is inverse tangent of x. In other words, we have just proved that inverse tangent of x has power series, or I should say Maclaurin series representation x minus 1/3 x cubed plus 1/5 x to the 5th, and so forth. It's pretty neat. All right, so in the last example, we were given a series and asked to identify which elementary function is representative. It's more often the case that we'll begin with some elementary function and ask for its power series. Bad use of its power series expansion. A function that has a power series representation is called analytic. All right, enough name calling. Let's get on to it. So find a power series representation of the log of 1 plus x equals to f of x. Well, we remember that differentiating the log gives us 1 over 1 plus x. And see, our goal is by one thing or another to get to something like 1 over 1 plus something, because then we can do geometric series on that, all right? So the derivative of log is 1 over 1 plus x. So f prime of x is equal to that by the geometric series again. A equals 1, r equals minus x. Great. Then I integrate term by term and evaluate it 0. Again, the constant 0. Don't want to give you the wrong idea. The constant doesn't always have to be 0, but just happen to be 0 in my examples here. And there we have it. Natural log of 1 plus x is x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th, and so forth and so on. Oh, hey, this is a good time to mention. I have mentioned before that the alternating harmonic series has converges to the natural log of 2. You can see why that is here. If you plug in x equals to 1, what happens? X equals to 1. We get 1 minus 1/2 plus 1/3 minus 1/4 dot 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 equals the natural log of 1 plus 1, which is 2. Right? So that suggests that the natural log of 2 is the thing to which the alternating harmonic series converges. All right. Although that is right on the edge of where this calculation makes sense, right? Because this is centered at 1, and the absolute value of r being less than 1 gives us 1, so I mean, x equals to 1 is not actually guaranteed guaranteed by this calculation. In fact, 1 is not included up here, right? I mean, nth term test, right? Nth term test, you plug in 1 here, you get, it doesn't exist, right? But when you integrate, something neat happens. Integrating actually adds a endpoint to the rate, to the interval of convergence. So the derivative converges minus 1 to 1. The not included, neither included, but the integral includes 1, because at 1 we get an alternating harmonic series which converges, in fact, to natural log of 2. But anyway, let me get back to it. So here we go. Example 6. Find the power series expansion of 1 over 1 plus x squared. All right, 1 over 1 plus x squared. A little worried about that you can see that clearly. Let me rewrite it just to be sure we understand what I'm saying. 1 over 1 plus x quantity squared. All right. Now that's not quite geometric, but it's almost geometric, right? In the sense that if we integrate this, we get minus 1 over 1 plus x plus a constant. So great, that that we can do geometric series for, right? So the integral of f of x dx is equal to f of 0 is, I'm not sure what I'm doing here. Sorry, guys. Huh. I mean, I don't disagree that f of 0 is 1, but this is not f. This is the integral of f. Tell you what, let's just go on here. I think this, you could ignore this, all right? Anyway, the larger point here is that the 1 over 1 plus x minus 1 over 1 plus x is this geometric series. That's the integral. So to get back to the function, we differentiate the integral. when we differentiate, that mysterious 2 is gone anyway, and out pops the answer, 1 minus 2x plus 3x squared plus dot 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 dot. So let me just scratch that out. Scratchy, 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 scratchy. Scratchy, 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 scratchy. That is nonsense. Scratchy, scratchy, scratchy. Sorry. Well fixed anyway. Moving on. Example 7. Whew, so many examples here. Power series can help also with more formidable integrals. Well, this is kind of like my example 1 in that sense. Suppose we wanted to integrate inverse tangent of x over x. All right. Well, fortunately, we already found the power series of inverse tangent of x back in a previous example, right? We found it was x minus 1/3 x cubed plus 1/5 x to the 5th, and so forth and so on. And we can divide by x just like you'd think. And so we get 1 minus x squared over 3 plus x to the 4th over 5th, or 5 rather. So that's the derivative, right? The derivative of the integral is just the integrand, all right? And then, okay, great. Then to get back to the, of course, then we integrate term by term, all right, to get to f of x. Sorry, there's something about the way I'm presenting this calculation it's just messing with my mind. But anyway, that's probably a good place to stop since someone's calling me. There's also an example 8 here, which I will. Well, it's the same technique again. Okay. Anyway, I'll stop here.